Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The story of scientific discovery often unfolds with a dramatic flourish, a moment of sudden, paradigm-shattering insight. Yet, some of the most profound revolutions in human understanding begin with far more prosaic concerns. They emerge from the meticulous, day-to-day work of engineers and physicists tasked with solving practical, commercial problems. Such was the origin of radio astronomy, a field born within the formidable research division of the American Telephone and Telegraph Company, Bell Telephone Laboratories. Its genesis was a direct consequence of a corporate mandate of immense commercial gravity, and its reluctant father was a young, unassuming radio engineer named Karl Guthe Jansky. In 1928, Jansky, a recent physics graduate from the University of Wisconsin, accepted a position at the Bell Labs field station in Huntsville, New Jersey. This was the era of burgeoning global communication, and Bell Labs stood at the apex of technological innovation. The company was investing heavily in a new transatlantic shortwave radio telephone service, a venture promising to connect continents with the speed of light. The service, however, was plagued by persistent and frustrating adversary radio static. This cacophony of hisses, crackles, and pops, known collectively as atmospherics, could overwhelm a faint voice signal traveling thousands of miles, rendering expensive calls unintelligible and jeopardizing the entire commercial viability of the project. The directive given to the 22-year-old Jansky was therefore clear, direct, and entirely practical. He was to investigate the sources of this noise. His mission was to identify, categorize, and pinpoint the origins of the static that interfered with radio communications at short wavelengths, specifically around 14.6 meters. The environment at Bell Labs was one of disciplined, goal-oriented research. It was an intellectual crucible where fundamental physics was placed in the service of engineering and commerce. Jansky's supervisor was the distinguished physicist Clinton Davison, who, in a beautiful illustration of the lab's dual character, had recently provided experimental proof of the wave nature of electrons, work that would earn him a Nobel Prize. Davison's fundamental research existed alongside a relentless drive for practical application. It was within this culture that Jansky was expected to operate. His task was a piece of a larger corporate puzzle, a necessary step in refining a commercial service. The ultimate goal was noise abatement, and any investigation into the fundamental properties of radio waves was a means to the very specific end. To accomplish his assignment, Jansky required an instrument of unique capability. He needed an antenna that could determine the direction from which a radio signal arrived. What he designed and built was a testament to pragmatic engineering, an apparatus of ingenious simplicity that would become iconic. Dubbed the merry-go-round, the antenna was a massive structure, 100 feet in length and about 12 feet high. It was a Bruce array, a series of brass pipes and wooden frames designed to be highly directional, meaning it was most sensitive to radio waves arriving perpendicular to its longest axis. The entire colossal structure was mounted on a set of 4 salvaged Ford Model T wheels, which ran on a circular brick track. A motor and pulley system allowed the entire array to complete a full rotation every 20 minutes, methodically scanning the entire horizon. The antenna was connected to a sensitive receiver tuned to a frequency of 20.5 megahertz. The output of this receiver was fed to a pen recorder, which traced the intensity of the incoming signal onto a slowly scrolling sheet of paper. For months on end, this machine turned, day and night, in a field in rural New Jersey, listening to the sky. Jansky's work was a model of patient, methodical data collection. He would correlate the peaks of static on his paper charts with the antenna's orientation, meticulously logging the time, signal strength, and direction of each significant noise event. His logbooks became a comprehensive diary of the radio environment, a detailed record of the invisible chorus that filled the airwaves. In 1932, after years of continuous observation, Jansky was prepared to report his initial findings. In a paper presented to the International Scientific Radio Union in Washington, D.C., and subsequently published under the title Directional Studies of Atmospherics at High Frequencies, he outlined a clear classification of the noise sources. He had successfully fulfilled the core of his assignment. He reported that the static disrupting Bell's radio service fell into 3 distinct categories. The first 2 were precisely what he and his superiors had expected. Category 1 consisted of static from local thunderstorms, characterized by sharp, powerful bursts that corresponded to nearby lightning flashes. Category 2 was a more persistent crackle from the aggregation of distant thunderstorms, whose energy was carried vast distances across the globe. By identifying these sources, he provided Bell Labs with invaluable data, confirming that terrestrial weather was a primary villain in the struggle for clear transatlantic communication. His paper, however, described a third type of signal. It was different from the others. It was a faint, steady hiss, a sound he compared to the noise made by steam escaping a pipe. Its intensity was low, far weaker than the crashing static from thunderstorms, making it a secondary concern from a purely commercial standpoint. Yet, it possessed a peculiar quality that set it apart. While the noise from storms was erratic and variable, this third signal was remarkably constant, rising and falling with a smooth, predictable rhythm over the course of each day. It was a whisper in a sea of shouts. Having categorized the dominant sources of interference, Jansky had largely completed his engineering task. The major culprits were identified, yet this faint, persistent hiss remained an unresolved anomaly in his data, a quiet puzzle whose solution was still hidden from view. His initial work was a success in the world of radio engineering, a solid contribution to the practical science of noise abatement. The faint signal was a footnote, a piece of clean data from an unknown source, awaiting a deeper analysis that would carry Karl Jansky far beyond the terrestrial concerns of his employer. The successful classification of terrestrial and atmospheric interference might have marked the conclusion of Karl Jansky's assignment. From the perspective of Bell Telephone Laboratories, the primary engineering objectives were met. The dominant sources of static hampering transatlantic communications were identified, their behaviors characterized. Yet, for Jansky, the project was incomplete. The third type of static, that faint, steady hiss, lingered in his data as a profound and elegant mystery. It was a signal whose quiet persistence held a deeper allure than the chaotic crackle of thunderstorms. This whisper from an unknown source became an intellectual fixation, compelling him to continue his observations long after his formal duties were fulfilled. He transitioned from a communications engineer solving a company problem to a pure scientist pursuing a fundamental question. For more than a year, the antenna at the Hungal, New Jersey field station continued its slow, deliberate rotation. The merry-go-round, as it was affectionately known, completed a full circle every 20 minutes, scanning the entire horizon. Day after day, month after month, Jansky accumulated an immense library of data, with a pen dutifully tracing the signal's intensity in long rolls of paper chart. His work was a testament to methodical patience, a deep belief that within this vast collection of seemingly monotonous readings lay a pattern of profound importance. He was searching for the rhythm hidden within the noise, a rhythm that would betray the source's identity. His approach was grounded in the rigorous empiricism of a physicist, demanding that any conclusion emerge directly from the evidence, without preconception. The breakthrough came from an observation of exquisite subtlety. As he analyzed the daily ebb and flow of the mysterious hiss, he detected a small but unwavering discrepancy. The peak intensity of the signal, the moment when his antenna was pointing most directly at the source, arrived slightly earlier each day. The daily cycle of this cosmic static was consistently shorter than the 24-hour cycle of the sun. The deviation was precise, measurable, and relentless. The peak occurred approximately 4 minutes sooner with every rotation of the Earth. To a layperson, this 4-minute shift might seem trivial, a minor curiosity in the data. To a mind trained in physics and celestial mechanics, it was the key that unlocked the entire puzzle. Jansky understood the profound difference between a solar day, the 24 hours it takes for the sun to return to the same position in the sky, and a sidereal day, which measures the Earth's rotation relative to the fixed, distant stars, is approximately 23 hours and 56 minutes long. That 4-minute difference is the result of the Earth's own orbit around the sun. Each day, our planet must rotate slightly more than a full 360 degrees to bring the sun back to its zenith. Jansky's data showed that the radio source was operating on a sidereal clock. Its position was fixed against the backdrop of the celestial sphere. The source was unequivocally of extraterrestrial origin, located far beyond the confines of our solar system. This realization was a moment of profound intellectual crossover. Jansky, the radio engineer, had used his tools to stumble upon a deep astronomical truth. To verify and refine his findings, he sought the expertise of a colleague at Bell Labs, the astronomer and physicist Albert Melvin Skillet. Jansky presented his data, the charts showing the signal's strength and, most importantly, the evidence of the sidereal daily cycle. Skillet's contribution was to provide the astronomical framework for Jansky's radio observations. He helped Jansky translate his antenna bearings and signal timings into the language of celestial coordinates, using star charts to map the position of this invisible source onto the visible sky. Through careful calculation, correlating the time of peak signal with the known orientation of this highly directional antenna, Jansky was able to triangulate the source's location. The evidence pointed toward a specific region in the heavens. The cosmic hiss was strongest when the merry-go-round was aimed at the constellation of Sagittarius. In the context of early 20th century astronomy, this was a startling and deeply significant finding. Modern astronomers knew that the direction of Sagittarius lay along the plane of our galaxy, the Milky Way. More than that, it was the location of the galactic center, the dense, brilliant core of our island universe, a region crowded with billions of stars and vast clouds of interstellar gas and dust. The faint whisper that had puzzled the telephone engineer appeared to be emanating from the very heart of the galaxy. With his evidence consolidated and his conclusions confirmed, Jansky prepared to announce his discovery to the scientific world. In May of 1933, he published a paper in the Proceedings of the Institute of Radio Engineers. Its title was A Model of Scientific Caution and Precision Electrical Disturbances Apparently of Extraterrestrial Origin. The language was understated, the claims supported meticulously by the data from his rotating antenna. He proposed that the source of the radio waves was either the stars themselves or the interstellar matter concentrated in the direction of the galactic center. He had opened an entirely new window onto the universe, demonstrating that information could arrive from the cosmos in forms other than visible light. The immediate impact of this seminal work was surprisingly muted. The professional astronomical community, accustomed to gathering its data with photographic plates and optical telescopes, lacked the equipment and the conceptual framework to follow up on Jansky's discovery. Radio engineering was a foreign discipline, and the idea of a radio telescope was yet to be conceived. Bell Labs, while proud of its employees' scientific curiosity, saw no commercial application for studying star noise and consequently reassigned Jansky to other projects. For a time, his monumental discovery lay largely dormant, a fascinating but isolated data point in the annals of science. Yet, the paper did find its way into the hands of a few individuals who could grasp its immense implications. Chief among them was a young radio engineer and amateur astronomer from Illinois named Grote Reber. Reading Jansky's work, Reber recognized the dawn of a new science and became consumed with the desire to build a better instrument to listen to the sky, ensuring the faint cosmic whisper Jansky had found would eventually become a symphony dot, having pinpointed the cosmic origin of the static, confirming its source lay beyond the solar system in the dense star fields of Sagittarius. Karl Jansky confronted an even more profound intellectual challenge. The task evolved from celestial cartography to fundamental physics. He had located the whisper. What language was it speaking? His from the galactic center was a message, and he now sought to become its first translator, armed only with the scientific vocabulary of the 1930s. This next phase of his work reveals a mind grappling with a phenomenon whose true nature lay just beyond the horizon of contemporary theory, forcing him to construct an explanation from the established principles of his day. The intellectual toolkit available to a physicist in the early 1930s was powerful, yet specific. The universe was understood primarily through the lenses of Newtonian gravity and Maxwellian electromagnetism, refined by the new quantum mechanics and relativity. When considering the emission of energy from cosmic bodies, the dominant and most thoroughly understood mechanism was thermal radiation. The physics of this process had been elegantly codified by Max Planck at the turn of the century. Planck's law of black body radiation described with exquisite precision how any object with a temperature above absolute zero emits a continuous spectrum of electromagnetic energy. The intensity and peak frequency of this radiation are dictated solely by the object's temperature. Theater objects glow brighter and at higher frequencies, shifting from infrared to visible light and beyond. This was the physics of stars, of glowing filaments in light bulbs, and of the ambient warmth of any physical body. For Jansky, a physicist trained in this tradition, any unexplained celestial radiation would first and foremost be interrogated as a potential thermal signal. This intellectual framework formed the bedrock of his landmark 1935 paper titled Note on the Source of Interstellar Interference. In this publication, he moved from reporting a discovery to proposing a physical cause. His central hypothesis was that the star noise was the collective thermal emission from the matter residing in the Milky Way. He considered two primary sources for this radiation. The first was the stars themselves. While he knew from his own measurements that the sun was a very weak radio emitter, he reasoned from a principle of aggregation. The direction of the galactic center represents the line of sight to the greatest density and depth of stars in our galaxy. He posited that the faint, cumulative radio frequency glow from billions upon billions of distant stars, all acting as imperfect black body radiators, could combine to produce the steady hiss his antenna was detecting. His second, and perhaps more favored, proposed source was the interstellar medium, the tenuous gas and dust that fills the space between the stars. Drawing on the work of astronomers like Arthur Eddington, who had theorized extensively about the nature of interstellar matter, Jansky imagined this medium as a vast, diffuse gas. He calculated that if this gas were heated to a very high temperature, perhaps thousands of degrees Kelvin, by the radiation from nearby young stars, it would become ionized. This sea of free electrons and protons, a plasma, would then radiate thermally, its energy output governed by the same physical laws as a solid object. The sheer volume of this interstellar gas, extending for thousands of light years, could potentially generate a detectable radio signal, even if the gas itself was incredibly sparse. His calculations suggested that the energy levels he observed were plausible under such a model, providing a coherent physical explanation rooted in established thermodynamics. Jansky's reasoning was a model of scientific prudence and ingenuity. He took a completely novel observation and sought to explain it using the most solid and well-understood physics available to him. His hypothesis was logical, calculable, and entirely consistent with the astronomical picture of the 1930s. It represented the most rational explanation that could be formulated within the confines of his era, yet it contained a deep and subtle flaw, one invisible to Jansky and his contemporaries. The explanation was elegant, it was physical, it was plausible, and it was ultimately incomplete. The true mechanism generating the galactic hiss was a process of a completely different character, an engine of radiation whose existence was yet to be theorized in an astrophysical context. The signal was produced by a non-thermal process known as synchrotron radiation. This form of emission arises when electrons moving at speeds approaching that of light are forced to spiral along powerful magnetic field lines. The immense acceleration experienced by these relativistic electrons forces them to shed energy in the form of a continuous spectrum of intense radio waves. This is the physics of particle accelerators and cosmic violence, of supernova remnants, and the turbulent magnetic fields that thread through the galaxy. The Milky Way's core, far from being a placid collection of thermal emitters, is a dynamic environment where cosmic rays, the high-energy particles accelerated in stellar explosions, are ensnared by galactic magnetism. This reality was conceptually inaccessible in the 1930s. The field of high-energy astrophysics was in its infancy, and the idea of pervasive, powerful magnetic fields shaping galactic dynamics was an alien concept. The universe was still largely imagined as a clockwork mechanism governed by gravity and heat. Jansky's discovery was one of the very first empirical clues pointing toward a more energetic and complex cosmos, a universe filled with phenomena that classical thermal physics was unequipped to describe. His attempt to fit the observation into a thermal model was therefore unnecessary and brilliant dead end. He had detected the signature of a new physics with an instrument built for the old one. The discrepancy between his thermal model's predictions and his measured signal strength, which he himself acknowledged, was a quiet testament to this fact. The signal was far stronger than any reasonable thermal model could easily justify, a hint that some other, more efficient process was at work. Thus, Jansky's final major contribution to the nascent science was to provide its first foundational theory, a hypothesis that served as the essential starting point for all that would follow. By proposing a testable physical mechanism, he elevated his discovery from a mere curiosity to a genuine scientific problem. He had mapped the source and offered a theory of its operation. His work posed a clear challenge to the scientific communities. Here is a signal from the heart of the galaxy, and here is a plausible, if imperfect, explanation for it. The next step required verification, refinement, and the construction of new instruments designed specifically for this purpose. The stage was set for a new kind of astronomy, yet the actors were slow to appear, hindered by forces of institutional priority and disciplinary specialization that would leave the cosmic signal unattended for a critical period. A silence that followed Jansky's final paper was a product of two powerful, intersecting realities of the 1930s scientific landscape. He had unveiled a new window to the cosmos, yet for nearly a decade, almost nobody looked through it. The reasons for this fallow period reveal a great deal about the structural barriers to radical discovery. The delay stemmed from the pragmatic mission of his employer and the deep, almost unbridgeable, conceptual gap that separated the domains of astronomy and radio engineering. The cosmic hiss Jansky had so meticulously documented was left to echo in an academic void, its profound implications awaiting a mind uniquely equipped to hear them. The first and most immediate barrier was institutional. Karl Jansky was an employee of the Bell Telephone Laboratories, a subsidiary of the American Telephone and Telegraph Company. Bell Labs was, and remains, one of the most productive research institutions in history, yet its purpose was fundamentally industrial. Its research, however exploratory, was ultimately tethered to the corporate objective of improving telecommunications technology and services. Jansky's original assignment was a perfect embodiment of this mission to identify and characterize sources of noise that interfered with the company's new shortwave transatlantic radio telephone service. He had fulfilled this directive with spectacular success. By identifying the primary source of the persistent hiss as a signal of extraterrestrial origin emanating from the center of the Milky Way, he had effectively solved the problem from Bell's perspective. The noise was cosmic. It was a fundamental feature of the universe, and therefore it was beyond their power to eliminate. For the engineers and executives at Bell, the case was closed. Their research had yielded its practical result. Pursuing the astronomical implications of the discovery, however fascinating, fell far outside the company's commercial mandate. This was an endeavor for observatories and universities, a matter of pure science with no foreseeable return on investment for a telephone company. The starkest evidence of this corporate posture came in response to Jansky's own ambitions. Energized by his findings, he drafted a formal proposal to build a new, far more capable instrument. He envisioned a large, steerable parabolic dish antenna, 30 meters or roughly 100 feet in diameter. Such a device would offer vastly improved sensitivity and directional precision, allowing him to map the cosmic radio sources with unprecedented detail and perhaps even detect fainter, more distant signals. The proposal was a visionary leap, outlining the essential design of the modern radio telescope. Bell Labs management reviewed the plan and declined to fund it. Their decision was entirely logical within their own framework. They were in the business of communication, and Jansky's proposed astronomical observatory promised little to advance the cause. Consequently, Jansky was reassigned to other, more conventional engineering projects within the company. The world's sole expert in the brand new field of radio astronomy was directed away from his own discovery, his pioneering momentum halted by the very institution that had enabled it. The merry-go-round antenna was eventually dismantled, and the cosmic signal it had detected was once again left to arrive on Earth unobserved. The second, more systemic barrier was disciplinary. In the 1930s, the field of astronomy was an entirely optical pursuit. The astronomer's craft was one of glass lenses, polished mirrors, photographic plates, and spectrographs. Their expertise lay in interpreting the light captured by these instruments, analyzing stellar spectra, and measuring the positions and motions of celestial bodies. The language of their science was that of optics and mechanics. Jansky's work, conversely, was written in the language of electronics. It spoke of antennas, receivers, amplifiers, and electromagnetic interference. His apparatus was a product of radio engineering, a field with which the typical astronomer had zero familiarity. This created a profound chasm. Astronomers did read Jansky's papers and publications like the Proceedings of the Institute of Radio Engineers and appreciate the startling conclusion, but they possessed neither the theoretical background nor the practical skills to build the necessary equipment to verify or extend his work. It would be akin to asking a master shipwright to construct a locomotive. The underlying principles of movement are shared, but the specific knowledge and tools are entirely different. They were astronomers, experts in photons of visible light, and what Jansky had found was a universe speaking in radio waves, a completely alien dialect. The engineers who could build the instruments had their focus directed toward terrestrial applications, while the astronomers who possessed the cosmic curiosity were unequipped for the engineering challenge. The new science was an orphan, claimed by neither discipline. For several years, this impasse held. The discovery was known, published, and even reported in the popular press, yet it failed to ignite a research program within the established scientific community. It required a unique individual, someone who could stand with a foot in both worlds, to bridge the divide. That individual was Grote Reber. Reber was a fascinating figure, a brilliant radio engineer who worked for a Chicago-based radio manufacturer and was also a deeply passionate amateur astronomer. He was a perfect synthesis of the two disparate fields. In 1933, he encountered Jansky's publications and immediately grasped their immense significance. He understood the astronomy, and crucially, he also understood the electronics. He saw with perfect clarity why the professional astronomers were unable to proceed, and he recognized the institutional constraints that had sidelined Jansky himself. Where others saw an insurmountable barrier, Reber saw a challenge and an unparalleled opportunity. If the professional institutions were unwilling or unable to build the next great instrument of cosmic exploration, he would simply do it himself. With his own funds and on his own time, Reber set out to solve the problem of instrumental access. In 1937, in the backyard at his home in Wheaton, Illinois, he began construction on the world's first purpose-built parabolic dish radio telescope. It was an extraordinary act of individual initiative. The design was entirely his own, a 9-meter, or 31.4-foot, paraboloid sheet metal mounted in a fully steerable altazimuth frame. This was a radical departure from Jansky's wire antenna. Reber's parabolic dish was specifically designed to focus incoming radio waves to a single point, dramatically increasing its sensitivity and resolving power. It was the prototype for nearly all future radio telescopes. Reber's motivation was explicit and directly linked to his predecessor. He was driven by a scientific imperative to confirm Jansky's detection of radio waves from the Milky Way, and then to systematically map the radio sky with a resolution far exceeding what Jansky's antenna could provide. He was picking up the intellectual pattern that Bell Labs had forced Jansky to drop. For 4 years, Reber designed, built, and refined his backyard observatory, a solitary figure working at the absolute frontier of science. He was a one-man research program, embodying the fusion of engineering prowess and astronomical vision that the field so desperately needed. His work represented the critical transfer of an idea from its initial discovery to its first dedicated instrumental pursuit, a transition facilitated by a single, determined mind. The solitary dedication of Grote Reber yielded its first profound results in 1940. Publishing in the prestigious Astrophysical Journal, he presented a coarse radio map of the Milky Way, a contour of cosmic energy that confirmed the essential finding of his predecessor. The emission was strongest from the galactic plane, peaking toward the constellation Sagittarius, the location of the galactic center. This publication, appearing in a journal read by professional astronomers, was a first crucial step toward legitimizing the field. 4 years later, in 1944, Reber published a far more detailed and comprehensive survey. This new map was a revelation. It showed with unprecedented clarity the structure of the radio Milky Way and, even more startlingly, identified discrete, powerful sources of radio waves away from the galactic plane. These observations pinpointed what would later be identified as Cygnus A, a distant radio galaxy, in Cassiopeia A, the remnant of a supernova within our own galaxy. Reber's work accomplished what Jansky's initial report could have achieved with institutional support. He provided systematic, repeatable data collected with an instrument built for astronomical inquiry. He spoke the language of contour maps and celestial coordinates, translating Jansky's faint hiss into a visual geography of a previously invisible sky. The professional astronomical community, which had greeted Jansky's findings with a mixture of curiosity and deep skepticism, could finally engage with the phenomenon on its own terms. Reber's backyard dish had single-handedly vindicated Jansky and laid the foundational charts for a new celestial cartography. The full blossoming of radio astronomy, however, awaited a global cataclysm. The technological crucible of the Second World War accelerated the development of radio and microwave technology at a breathtaking pace. The urgent need for sophisticated radar systems to detect enemy aircraft and ships drove immense investment into high-frequency receivers, powerful transmitters, and large antenna arrays. When the war ended, a generation of physicists and engineers possessed an intimate familiarity with this advanced equipment. In Britain, a group led by James Stanley Hay, using captured German Wolfsburg radar dishes, detected intense radio bursts from the sun correlated with solar flare activity. This discovery, made while investigating sources of radar jamming, echoed the serendipity of Jansky's own work. The tools of war were being turned toward the cosmos, and the surplus of technology and expertise created the fertile ground for the explosive growth of a new science. Laboratories and observatories sprang up across the world, from the Netherlands to Australia, all populated by veterans of wartime radar projects who now applied their skills to the sky. As the field matured, its practitioners sought to honor its quiet founder. The most fundamental tribute is woven into the very fabric of the science. The basic unit of spectral flux density, a measure of the strength of the cosmic radio source, was named the Jansky, abbreviated JI. 1 Jansky is equivalent to 10 to the power of minus 26 watts per square meter per hertz. The infinitesimal smallness of this unit is a permanent testament to the extraordinary sensitivity required to listen to the universe, and a profound acknowledgement of the man who first detected such faint whispers. His name is now spoken daily in observatories worldwide, a constant reminder of the field's origin. A more monumental tribute stands on the plains of San Agustin in New Mexico. The Karl G. Jansky Very Large Array, or VLAR, is one of the most powerful and iconic scientific instruments on Earth. Its 27 massive radio antennas, each 25 meters in diameter, work in unison as a single, continent-sized telescope. The VLA embodies the principles of interferometry on a scale its namesake could scarcely have imagined, producing images of the radio universe with astonishing resolution and clarity. By dedicating this premier instrument to his memory in 2012, the scientific community offered its ultimate acknowledgement. The engineer from Bell Labs, who was once reassigned from his cosmic static, now has his name affixed to the instrument that represents the pinnacle of the discipline he inadvertently created. The legacy of Karl Jansky is therefore the entirety of modern radio astronomy. The discovery of quasars, the hyperluminous cause of ancient galaxies, was a triumph of the radio window. The detection of pulsars, the spinning neutron stars that act as precise cosmic clocks, was made possible by the unique capabilities of radio telescopes. Perhaps most profoundly, the discovery of the cosmic microwave background radiation by Arno Penzias and Robert Wilson in 1965 was the ultimate echo of Jansky's work. They too were Bell Labs engineers, using a sensitive horn antenna to eliminate a persistent omnidirectional hiss. That hiss was the afterglow of the Big Bang itself, the most important cosmological discovery of the 20th century, and it was found through the same process of meticulous noise elimination that Jansky had pioneered 3 decades earlier. Karl Jansky's story is a powerful meditation on the nature of scientific progress. It illustrates the profound role of serendipity, where the search for a solution to a practical engineering problem yields a discovery of fundamental importance. His experience reveals the inherent friction between the directed, application-focused goals of industrial research and the unpredictable, curiosity-driven path of pure science. Bell Labs sought a clean channel for transatlantic communication. Jansky delivered a channel to the cosmos. He was a reluctant pioneer, an engineer who performed his assigned task with such diligence that he stumbled across a new reality. He saw the astronomical significance of his findings and wished to pursue them, yet his path was redirected by institutional priorities. His life was short, and he would see little of the incredible scientific revolution he set in motion. He remains a figure defined by a singular foundational achievement, the faint, persistent hiss he isolated from the crackle of terrestrial thunderstorms was the opening note in a symphony of cosmic discovery that continues to unfold. It was the sound of the universe announcing its presence in a new spectrum, a form of light our eyes were blind to. Karl Jansky's great contribution was teaching humanity how to listen. The science he founded continues to widen that channel, revealing a universe more dynamic, violent, and intricate than we ever knew, all stemming from the patient work of a man trying to solve a problem with static.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.